Good morning, Year 11s. How's it going, guys? Thanks for coming along. It's nice to see everyone there. Whoa, loads of people on the chat. Boom. Look at that. That's great. That's awesome. Just gonna, yeah, look at that. Finally, I'm first. Yeah, you weren't, Ben. Whoops, wait, no. That's amazing. Love it. Right, guys. So I've actually called this lesson 6. I think it's meant to be lesson 7 on YouTube. But this is the final lesson of equilibrium. So we get to box it off now, which is nice. And then we can start looking at some exam questions for some homeworks. And then you guys are going to have your test on equilibrium. Okay, so let's crack on. Share screen. Oh, I'm going to close my YouTube window down because I've popped out the chat, so that's there. I can still see it. RIP Ben. Love it from Rue. Right, let's crack on. So today's lesson. Let's fold my screen into a tablet. Okay, so equilibrium lesson 6, and apparently this is actually lesson 7 according to YouTube. Yeah, it doesn't surprise me that I'm out of sync by a couple because I'm juggling it between the two classes. So 3 learning objectives: no direct hydration, no contact process, understand flow diagrams. So it's quite nice just to look back at the previous lesson because we were doing this and I didn't get to be able to use the flow diagrams. We talked about the compromise and we did the Haber, and we had these other 2 processes that we're then going to look at today. So industrial equilibrium. So first one, direct hydration. So let's put our title in. That's definitely not what I wanted. Let's try that again. Yeah, direct hydration. Okay, so direct hydration, the process used to add H2O gas, so steam, to add steam to an alkene. To an alkene forming an alcohol. So let's look at the equation. We take ethene, and ethene is a gas. Take ethene, and we're going to add to it steam. To add H2O gas. It's nice to have our state symbols because you need them. Equilibrium, reversible even, I shouldn't do that. Reversible, yeah, ethanol. Now what I'm actually going to do is I'm actually just going to color code this for a minute. Yeah, I'm just going to color code this, just to show you what's actually happening in terms of the atoms. So if I just color code the water, if I go H, okay, that's a bit much. Still too much. I'm going to stick with the pencil. I quite like the pencil on this tablet. So H, and then green. I quite like the pencil look. Green, and then O. No, I'll color code everything. Color code the lot. Orange, and then purple, color coding everything, and then dark blue. Perfect. So where do all of these things now go? So what now happens is that you break one of the bonds in the steam. One of these bonds will break. I'll choose him. Yeah, and what will now happen is that H has gone on there. The red H drops onto that guy. So that red H has gone to here. And now the rest of the section, this entire bit here, suddenly realized I didn't really need to color code all of that bit, goes there. So what I could have just done is I could have just color coded that like that. That would have actually been much better. That's better chemistry. Prefer that. There we go. And I'll do that one there as gray maybe. There we go. So the 2 sections, you realize we're breaking the double bond. By the way, we're producing ethanol, of course. This is steam and this is ethanol as a gas. There we go. So if you want this as a written equation, and that's nice to see what's happening in terms of bonds, we're breaking the double bond. Yeah, break double bond. That's why we love alkenes, by the way. Break CC double bond. And then what we do is we then add stuff across it. Yeah, add across the double bond. If you don't know what I mean by across the CC double bond, across the carbons. I'll just put across the carbons. Because essentially what happens, it's just nice to do this from an organic perspective. If you have a double bond, if you have a double bond, I'll draw this like this. By the way, this is totally okay, totally legit. It's just not something you'd usually do because it's a bit weird. If you have that molecule there, there's ethene, and I was to add something else to it, let's add something like X and Y. Let's add XY, to this. What's going to happen is it's going to break the double. It breaks the double bond, so it becomes a single, and you add the two pieces across it. One of them will gain an X, and the other one will gain the Y. You add it across the two people that you're adding in, a split, and go on opposite sides. So you can see what the water's doing. It's split in half at that point. You can't split an oxygen down the middle, of course. That's just silly. So you've got to split it one side or another. Oh, organics. So it's nice to talk about that. Add across the double bond. So we've now made steam. We've made ethanol. Let's turn this into a better equation. So switch back to black. So final thing is you can do that. C2H4 plus, and that's ethene, plus H2O gas, has to be special because it has to be a gas, and we're forming CH3, CH2OH. We're forming ethanol gas. Okay, so this is called direct hydration. So what are the conditions going to be for it? So first thing is temperature. We need to consider the temp. So I'm now going to tell you that the forward reaction is exothermic. There we go. This bit of data here tells us forward reaction. Forward reaction is exo, and we know it's exo because of that sign there. So on the chat, please. Do I want to raise it or lower it to make more ethanol? Do I want to raise it or lower it to increase the yield of ethanol? What would I like to do in terms of equilibrium? Hard question without you guys having the time to run coughs. Well done, Ben. Ben is absolutely right. Spot on. Well done, Con. You want to lower it. If the forward reaction favors hot, if that's hot, we want to cool it. We want to do the opposite of what the arrow says. So lower temperatures are better, but we need a compromise, because if we lower it too far, then the rate slows down. So temperature, compromise. We like this. So temperature, lower temps favor higher yield. So compromise temp is 300 degrees Celsius. Reasonable yield, reasonable yield, reasonable rate. That's what you write. If they ask you why do they need to have a compromised temperature, you just say, so they have a reasonable yield and a reasonable rate. So 300 degrees Celsius for this. Next, pressure. Okay, pressure. So I've got 2 moles on this side, and I have 1 mole on that side. What do I want to do to the pressure to increase the yield, please, folks? What do I want to do to the pressure to increase the yield of ethanol? You guys have done that so well. 5 people just nailed that. I'm really impressed. I know that I've not got comments from everybody, but, you know, it's nice to see that loads of people there. Ben is on this. Increase, spot on. Ben and Tom, well done. Ruby, increase, well done. We want to increase this. Well, look, you guys are on this. I'm doing something right. Pressure. Higher pressure favors favors higher yield, since more moles of gas, since fewer, you could actually have done it the other way around, but since less moles, what is wrong with me today? Less moles of gas on right. I like it. Okay. So can I just point out, I'm so impressed that you guys all got that. That's amazing. You didn't even run coughs. You're looking at it and you go, I get it. Oh my God, I'm doing something right. So what that means is we're going to crank up the pressure. Now there is a compromise here as well, isn't there? Because the problem is cost of equipment is high. However, in the Haber process, they use 200 atmospheres. Like, it's kind of an industry standard. Temp 450C, pressure 200 ATMs, terrifying, and catalyst iron solid. Yeah, powderized, greater surface area, all that jazz. Yeah. So this kind of here is kind of an industry standard. So what that means is most companies will just buy the same vessel that contains this. Yeah, the same vessel that contains this is sold to do lots of stuff. It can manage 200 atmospheres very easily. You know, it's an industry standard. So you'd like to think that you could go to 200 atmospheres on this as well, but we can't. And there's a limit here. There is another problem. The pressure in this case is 60 atmospheres. And the question is why? Did you know they actually use the same equipment as the Haber but they then just only take it up to 60 because it's cheaper to buy a vessel that's already been designed for something of a higher pressure than to have them design a brand new one that can only cope with their lesser pressure. Just buy the one that's already built and designed. Like, it's cheaper. But they can only take it to 60. Now, there is a reason for this. So why? The reason being is ethene. Ethene has a problem. Ethene gas. If you take ethene gas, I want to show you a really clever little equation here. Rather than drawing it out, if I take ethene, CH2, CH2, there's ethene as a structural formulae. If I take ethene and I take n number of them, n means many. So I've got ethene gas in a container, and I put this under pressure. So if I increase the pressure to 90 atmospheres, something very special happens. It polymerizes. And what you form is CH2. Isn't this bizarre? N. I could actually draw that out a bit better for you in reality. It's not the way you do it. The way I'd actually do this is this is where drawing it out has value, because you can see the difference between the two things. So I'll draw this out, and I'll draw it vertically like that as well. So here's the ethene at the beginning. Here's the ethene, and I've taken n number of them. And what now happens is the double bond breaks, and they join together to form polyethene. We'll be doing polymers later on in organics towards the end of the year, but it forms a plastic. And what that means is, can you imagine doing this whole game and then all of a sudden the gas in your tank turning into a solid blocks all your pipes and the whole thing explodes? It actually happened once. There was a mistake at a direct hydration plant in the United States where a pipe got blocked, which meant the pressure increased. And they didn't notice it on the gauge because the gauge, that was so stupid. They had a gauge that was measuring pressure. Yeah, they had like a little gauge like this. And you can imagine it being like, 0 atmospheres, like 10 atmospheres. Oh no, shouldn't do that. Like, I don't know, 50 atmospheres, 100 atmospheres, 150, 200. So the problem was, because they bought the same vessel that they used for the Haber, the pressure gauge was the same as well. Now, what that meant was, instead of the gauge reading 60 atmospheres, which is what it needed to read, yeah, a pipe got blocked. So when the pipe got blocked, the pressure increased. But the problem is the difference between making lovely drinkable ethanol, okay, we don't actually drink it, we use it as a fuel, but instead of like this here, this pressure here, yeah, this is good because we're making, it's not just good, it's needed. Yeah, this is what we need. But then the problem was if it reaches that, yeah, at that point it explodes. Yeah, explosion. And you realize that it's a really stupid dial because the problem was the difference is so small, like most people wouldn't even notice the difference. Yeah, and the amount, like, even though apparently it took quite a long time for the pressure to increase, but the problem was the difference was so small on the gauge that they didn't even notice. What they're meant to have done, so what they had to have done was to replace the gauge, yeah, to replace the gauge with a different scale. So instead of being 0 to 200, it was 0 to 100, yeah, and that was 50. So if it read there, so this now gave you, that's the explosion. The difference now becomes much more easily readable, yeah. And of course, these are all then flagged with their little colors, yeah, because you know these dials, you know, the dials are green. I should do this as like a highlighter. They're green all here, and then there's a yellow bit, and then there's the red bit. Yeah, they're color coded like this. And even the one that they had before, the problem was all the green bit, because the Haber process goes up to 200. So actually it was even worse than that because their gauge was more like going up to 400. Yeah, so that the window was even smaller. Like that would be 200 and that would be 300. You know, it was really ridiculously small. And the problem was their green area is up to here, and then their yellow area was, so the problem was the explosion happened. The explosion happened because it was still within the green section. It was an absolute fiasco. It caused quite a lot of deaths, I believe, as well. Like the whole plant, like there was a massive explosion. One of the tanks exploded, and yeah, and the ethene then, of course, luckily it became solid. But the ethene and the pipe, some of it caught fire because it's a hydrocarbon. They burn. It's terrifying. So you have to remember 60 atmospheres, and the bullet points to remember is will polymerize at 90 atmospheres. Yeah, if they say why only 60, you just simply say 1 mark, it will polymerize at 90 atmospheres. Or you don't even have to remember the 90, by the way. It will polymerize at higher pressure. There you go. You don't even need to know the number. Yeah, cool. Right, we need a catalyst. Last bit, and then direct hydration's done. Catalyst. The catalyst is phosphoric acid, concentrated phosphoric acid. If you're interested, H3PO4. Here we go. And that, you just have to know them, guys. Just spit them out. Needs a catalyst. The catalyst doesn't change the position of equilibrium. We don't get any more yield, but we do it at a faster rate. Yeah, so you make it, you get through each cycle faster. Cool. Next, right, so direct hydration. Boom, done. Direct hydration, finished. Making ethanol. By the way, just to mention, ethanol, yeah, uses of ethanol. Number 1, top answer, fuel. You are not allowed to say we drink it. Please don't. It's not okay. Yeah, the other one is you're allowed to say sterilizing agent. Sterilizing agent. You're allowed to hand sanitizer. Yeah, totally okay. But fuel is the top answer. We make millions of tons of ethanol every year, and 95% of it goes to make fuel. It goes into petrol, makes it burn better. Next. Okay. Right. Underline. Contact process. So this is used to make sulfuric acid, H2SO4. I like it. Oh, by the way, I just want to show you the flow diagram of the direct hydration plant. Direct hydration. I should be linking these in all together. No, not propylene. Just put direct hydration. I should have put ethene. Images. There it is. Right, I'll open that, and then because it might give me a slightly better quality one. There we go. Sorry, it's going to be if I do that, and then I can just screen snip it maybe. Come on, clean it up. There we go. And then I'll screen snip this. There we go. Edit, copy. Okay, just to show the flow diagram before I move on. Cool. So we know that similarly to the Haber process, yeah, they recycle anything that's unused during the process. There we go. 300 degrees Celsius, 60 to 70 atmospheres, phosphoric acid catalyst. Okay, cool. And then anything here. So we are recycling. The flow chart here is we are recycling unreacted gases. Yeah. And this, of course, saves money. You don't want to just release unreacted things into the atmosphere. You don't have to deal with them. Recycling them is far, far better. Yeah. We also need to talk about the recycling of heat energy as well. I'll show you that in another flow diagram in a minute. But it's nice to see the flow diagram and the recycling of resources. Right, so the contact process. So what are we doing here? Now, this one, guys, I'm going to run all the way through, and then I'm going to say, but the only bit you need to know is this. But then I'm going to show you the Edexcel question where they did actually do this. So in order to make sulfuric acid, we want to make him. So how do we do it? First of all, we're going to go and buy solid sulfur. I'll do it in black. We're going to buy solid sulfur. So we're going to take the sulfur from the volcanoes. We buy them from the guys on the volcanoes. We take the sulfur and we burn it to make SO2. And that's a beautiful reaction. It actually burns with a beautiful blue flame. Really, really pretty, that reaction. If you're interested, look it up. Go onto YouTube and look up sulfur fires, and they're beautiful. So it's the sulfur burns in oxygen to form SO2. And that is non-reversible. Yeah, it's unidirectional. Then what we're going to do is take the SO2 and we're going to react it with more oxygen. And this is now reversible. And we're going to form sulfur trioxide. There we go. Right, now we've got the sulfur trioxide. We're going to take the sulfur trioxide and we're going to add that to sulfuric acid. And what that forms is what's called oleum. That forms oleum, otherwise known as, commonly called, fuming sulfuric acid. Terrifying stuff. Like, wowzer, is that stuff dangerous. Crazy dangerous. So now we've got oleum. What we now do is now take oleum, and everyone's at this point freaking out, like, do I need to know all these equations? No, you'll be given them. You then add water, and it turns into 2 sulfuric acids. Like that. There we go. And that's the final process. So at the end of it, you double the amount of sulfuric acid you had originally. You then tap half of it off, run the other stuff back to go into the second step again, and you keep making it in a continuous kind of recycling them through. It's really clever. Take half out, put the half back in, doubles it, take half out, put it back in. It's cool. So what we now need to realize is there's only one equation here. There's only one equation here which is reversible, and that's the one we're going to need the conditions for. So, question. I need to tell you that the forward reaction is exothermic. I'll put it in red. Seems reasonable for me to do that. Minus delta H. So what am I going to want to do to the temperature? You kind of get the point of this, don't you? Let's get the flow diagram. All I actually need is that one. There we go. Oh, I don't want to take. Oh, I prefer that one. That's much nicer. That's the Haber process. Sulfur dioxide. I prefer that one. That one's better. Yeah, let's take that. Like it. Copy. Paste. Right. Come on. Come on. There we go. Flow diagram. Suddenly realized it's told you the answers to all my conditions. Not that it matters. It's fine, it's fine, it's fine. There we go. So, temperature. What's great is it's the same temperature as the Haber. That's really handy. But notice the pressure. The pressure is 1 atmosphere. That's interesting, isn't it? Because what would we want to do to the pressure for this reaction? What would we want to do to it? So guys, you can add this to your notes. Add this box here to your notes. There we go. I like it. So what's odd is, so the temperature is a compromise again. So conditions, let's add the condition. I'll write it with you. It's only fair. I like writing everything with you. Yeah. Conditions for contact process. 450 Celsius, the same as the Haber. That's really handy. It's a compromise again. Yeah. Reasonable rate, reasonable yield. Yeah, it's a compromise. Reasonable yield. Right. Pressure 1 to 2 that's temp. Yeah. Pressure 1 to 2 atmospheres. That's strange. Why? 1 to 2. I actually preferred 2, by the way. I preferred 2 atmospheres because it tells you that they do tend to do it. Wait, Mr. Duncan, if the forward reaction is endothermic, it's not. The forward reaction is exothermic. Ben, it's exo. Remember, it's minus exo. Yeah. It's exo in the forward direction. It's a combustion. You're reacting with something with oxygen. It's going to be exo. Yeah. 2 atmospheres. This is weird. Huh? Yeah, just like the 60 atmospheres with direct hydration, possibility of it polymerizing and exploding, blocking pipes. This one is actually, no, I mean like, what if the forward reaction is endo? Oh, then you would raise the temperature. Absolutely, Ben. If the forward reaction was endo, I'd increase the temperature to have a higher yield. Yes, Ben, you're absolutely right. Yes. Yes. This one is as simple as yield already at 90%. No point buying expensive equipment that will need to be replaced every year, every 10 years even. Expensive equipment for an extra, what, 5%? Yet remember, you can never push it to the 100. So we've only really got 1 to 9 that you're going to get more of. But to get that extra is going to cost you huge amounts of money. It's just not worth it. Just recycle it. It's just not worth it. Yeah, for the extra 5%, they don't bother. The catalyst is V2O5, vanadium pentoxide, and that's it. It's the end of industry. It's the end of industry. I want to have a look at a flow chart just to show you a couple of things. Don't want to rush you guys. You can pause the video there if you want to make those notes. So just to show you this cool flow diagram that I stole. Yeah. What's really clever about this is that there's lots of, so when you get given a flow chart in your exam, I will actually include some of these in your next homework for revision, some of these flow diagrams, because their questions are quite clever. They give you a flow diagram and they ask you, what they do is they label the pipes. They'll label this one as pipe A, and this one as pipe B, and this one as pipe C, and this one as pipe D, and this one is pipe E. And what they do is they say, look at the flow diagram and identify a pipe that is recycling, recycling materials. Yeah, and you'd go, oh, hang on a minute. I'm getting down here as my product. Oh, this is direct hydration. Ah, isn't that nice? And that's the ethanol output. This down here is the ethanol output. Yeah. And what we realize is that this one here, that pipe there is recycling the unused ethene. So I'd say E in terms of one that's recycling materials. Yeah. Why is this good for the environment? Because it's a non-renewable resource. We know that any alkane is a hydrocarbon. They come from crude oil. They are non-renewable. Yeah. By recircling it, you're saving non-renewable resources. Yeah. The next one, so the two questions of flow diagrams that tend to be, these are the, and we can add this to our notes actually, flow diagram questions. I think that's got value. Right, so flow diagrams. So question number one. Question one. Identify on flow diagram. Pipe, maybe. They could say it in different words. They could just say, they're usually labeled. Yeah. It might say circle the pipe. Yeah. Identify on flow diagram. The pipe or part. Yeah. Part showing recycling of materials. Yeah, recycling of, and notice my capitalization now. Yeah, materials. Because in these flow diagrams, there are two things that we often see. So one is the recycling of the material, which was pipe E. Is there any others in this particular one? So we've got something going on down here. Look at the catalyst. So we're inputting in our ethene. Look, there's a downpipe. But this is, so the ethene's coming in and then it's coming up here. And it's going into this heat interchanger. And then it's running then from there up through here. And then it's going into the mixer where steam's being added. That then enters the catalyst chamber where it comes out. And that's interesting. It then passes back through the interchanger. Why would they be doing that? What's the function of it going back through the interchanger? And this is the second question, which is, we can see recycling of materials in terms of this pipe here, but there's another recycling, and it's the recycling of heat. We know that this reaction is exothermic. Yeah, it's exothermic in the forward direction, and we're heating this to 300 Celsius. Well, when the products come out, they're coming out as hot gases. Well, what they can do is they can use that gas and recycle that heat and put it back into the ethene in the heat interchanger. So there are also, it's nice to just put this as the second question, identify on the diagram, question 2, identify on flow diagram, recycling of heat. Recycling of, they don't tend to say heat, they just tend to say energy. But it's very clever, like you see these. So one is recycling materials, and the other is the recycling of energy. The energy is usually harder to find. What you will look for is you look for these ideas where heat pipes are running nearby each other. Mr. Duncan, can you please post the flow diagram picture on the Google Classroom? Yes, of course I can. Absolutely, Shan. I have a screenshot. Should I put it on the Hangout? Yeah, that'd be lovely. Thanks, Ruby. That'd be amazing. Yeah. That brings us to the end of equilibrium. So just for fun, since my lesson, how much time have we got left? How are we doing for time-wise? I think I'm okay for time, right? There's Ruby posting her picture, which is amazing. Thanks for that, Rubes. Really appreciate it. So this lesson ends at 10 o'clock on the dot. So what it's nice to now do is just do GCSE, Edexcel, chemistry, specification. It's really nice for me to go to the specification, and we can have a look at the equilibrium section and just check that we have done everything. Chemical tests, energetics, rates of reaction, and equilibrium. There we go. Right. So know that some reactions are reversible, and this is indicated by the following symbol. I'm going to screenshot this, guys, full screen snip. Let's tick them off. Right. So definitely got number 1. Describe reversible reactions such as dehydration of hydrated copper 2 sulfate and the effect on ammonium chloride. Guys, it's the end of my lesson today. Know that the reversible reactions can reach a dynamic equilibrium in a sealed container. There's the closed system. Know that the characteristics of the reaction at equilibrium are the forward reaction occurs at the same rate and that the concentrations of reactants and products remain constant. Understand why a catalyst does not affect the position of equilibrium because it increases both the forward and backward reactions equally. Know the effect of changing either temperature and pressure on the position of equilibrium and run COFs for all of them. Reference to Le principle not required, which is great, which is awesome. We just run the COFs and we're good. Right, perfect. Okay, guys, let's now, one more thing. I like it. So this is kind of a specific thing for Edexcel. So this is just a last bit, kind of an extra. So equilibriums, Edexcel, what am I doing? Edexcel likes. Okay, so number one is you learn in diffusion. You learn in diffusion in year 7. You learn that we do this demonstration where we add hydrochloric acid there, liquid, yeah, concentrated to boot, it's nasty stuff. And we add that into a tube, and then we add concentrated ammonia, yeah? And what we then get to do is see the diffusion process. And what we always notice is that in terms of distance traveled, the hydrochloric acid always travels around about a quarter of the distance compared to the ammonia. And what you get is a white ring, yeah? You get a gray ring about there. It's closer to the HCl. Yeah, traveled that distance in that time. Travel in time. You've got to state both of them in the answer. Travel distance in this time. Travel in time. Yeah, and the reason being is it weighs 36.5. It's very heavy. And then ammonia has traveled that much distance. NH3 travels further, travels more distance. Yeah, in the same time. Yeah, and the reason being is because ammonia weighs 17. Yeah, different MRs. It's lighter. It's going to diffuse more quickly. Yeah, I've got lots of questions coming through and I don't know why. Mr. Duncan, could you please post the pic on the Google Classroom? Yes. Does anyone have the one with the pipes where Mr. Duncan labeled them? Guys, I will post all those flow diagrams. If you on the Google Classroom, you can just Google them alternatively and they're there. Like, try not to freak out here, guys. It's not the end of the world. I got them on Google. You can get them on Google. But I'll do the ethanol one, the big complicated ethanol one, because it's kind of a cool picture. I will post it on the Classroom as soon as I'm done. Yeah. Now, the reason why this is important for Edexcel for equilibriums is this equation, this reaction between ammonia, which is a base, by the way. It's nice to do this. Ammonia, pH 11, which is a gas, yeah, is going to react with HCl, which is an acid. Change to red. HCl, which is an acid. That's a gas as well. Yeah. And what it's going to form in equilibrium is it's going to form ammonium chloride, which is the salt, which is neutral. Yeah. Ammonium chloride. And that's a white solid. Right. Now, the whole thing is that this whole thing is actually in equilibrium. Yeah. What I can do is I can turn this white solid back into the gases. And we can actually label the information. So that reaction, by the way, notice that they're combining together. Yeah, so this is like an addition reaction. It's actually a neutralization reaction. But it is exothermic in the forward direction because bonds are being made. Yeah, we're making bonds. So this is exo. Yeah, it's nice to label all these things. It's exo here. And then, of course, endo here. So if I increase the temperature, what's going to happen is I'm going to drive it back this way, and the solid will break apart again. Yeah. So what you can actually do is you can do a rather interesting, an interesting demo with this, because what you can do is if you get a long tube, this is why I need to try and figure out how I'm going to draw this. If you get yourself a really long tube, like that, and at the bottom, what you do is you've got to create a cork seal, which is a bit of a nightmare. But what you do is at the bottom, you use a glass slide and you seal the bottom and you add your white solid at the bottom. Yeah. Now that white solid down here, that there is ammonium chloride solid. Right. And then what you do is you heat it. If you heat it up from the bottom, when you heat it, you push the equilibrium back in the endo direction. Yeah. And what will happen is it will turn into gases, into an invisible gas. It'll turn into HCl and ammonia. But then if you've got a tall enough jar, if you've got a really tall, sometimes you do this in a gas jar, that actually works quite well. And what happens is they will travel up here, but as they're rising up the tube, they're cooling down. Now, when they cool down, all of a sudden, the solid reappears. Yeah, the solid suddenly reappears as smoke. So what's happening is in the middle, there's nothing at all because the gases here, these are invisible gases. Yeah, invisible, colorless gases. So, but the point of the tube is the fact that it's cooling down. It's hot, it's adding a gradient, hot at the bottom, and then it's cooler at the top. I'll put cool. And what of course happens is the equilibrium, when you heat it up, you push the equilibrium, so you can actually look at this in stages. You can take the white solid of ammonium, it's a bit stupid, of ammonium chloride, you can heat up this solid and you will drive the equilibrium that way because that's the endothermic process, breaking bonds, mexobendo. Yeah, you'll push it that way. What will then happen is you will form colorless ammonia gas and colorless HCl gas, and you see nothing. And then, of course, so this is the heating process. You heat it and you drive it that way. But then as they rise up the tube, they cool down and the reaction then goes back again. So you end up with this rather weird setup because you can actually see this kind of cycle of equilibrium just by heating the bottom of it. It's quite entertaining. So you've got to know about that one. The other one that Edexcel needs you to know is anhydrous copper sulfate. So we know that anhydrous copper sulfate is a white powder and it is used as the test for water. Yeah, it's the test for water. So this is anhydrous copper 2 sulfate, and it is white. Yeah, formula CuSO4, solid. Yeah, and it is white. So what we then can do is we can then add water to it. Yeah, we can now add some water. My amazing diagrams. Okay, I've ruined that. Oh, I was doing so well. So well. There we go. Add some water. Yep, add a drop of water. And of course, what happens is, I can make that into some kind of a pet, not that it really matters. Yeah. So you add some water, and what happens is the water, of course, is colorless. Shouldn't really do that because it's a little bit confusing. Yeah, I don't like that anymore. Yeah, let's just move him out the way. Oh, that didn't work at all, did it? Come on, Mr. Duncan. Not doing very well now. I just want to move him. There we go. Oh, I've moved all of it. Doesn't matter. So you add your colorless water. And of course, when you add the water, it turns blue. Yeah, the whole thing it'll just turn bright blue. And the reason being is here's the equation. CuSO4 plus 5 H2Os. That's liquid and that's a solid. And it then forms in equilibrium. It'll form blue CuSO4.5 H2Os. And the whole point of the equilibrium is that if you add water add water, yeah, add it, the equilibrium will shift to the left to right. It'll shift to remove it. But then if we heat this, step number 2, if we heat that, yeah, we are going to push the equilibrium back in that direction and drive away the water. So they like these two. They're two particular equilibriums, and for them to mention them specifically on their specification, it is definitely worthwhile you discussing it. And you'll see these appear regularly in past papers. So I will tick off that one now. Oh, on my screenshot. There we go, for both of them, which is great. All discussed. Guys, that brings us to the end of equilibrium. We are done, which has been loads of fun. Really enjoyed it. We are finished, and your test is going to be... When's your test? Your test is on... Your test is on Tuesday. I will set you some questions on the classroom for you to do your revision with. I'll include the mark schemes and have a go at them. But your test is on Tuesday, guys. We're done. I hope you have a nice weekend, everybody. Take care. Be safe. I'll see you all soon.